Hi, I'm Ivan Savelyev from the Naval Research Lab. My talk is about field observations of the frontal microstructure variability at the north wall of the Gulf Stream. This is still an ongoing field study, and here I will overview the kind of measurements that we're collecting, and we'll also share some early data analysis results. The papers that motivated this study include theoretical work by Leif Thomas, where they identified various types of frontal instability, and also other investigations by means of idealized numerical simulations where they have demonstrated what those instabilities would look like. For example, the gravitational instability, the inertial instability, or the symmetric instability. For this symmetric instability case, we were flying over the Gulf Stream a few years ago, and we saw what we think might have been a surface footprint of this symmetric instability. So, motivated by these findings, we decided to come back to this study area with a more systematic approach to have multiple observations in different conditions and hopefully detect some of these instabilities in their various stages of development. For the study area, we chose the point where the north wall of the Gulf Stream separates from North Carolina shelf and becomes a deep water free-flowing current unconstrained by bathymetry. This location is advantageous because it provides a reliable deep water front, but also at the same time it's close enough to shore so that we can reach it by a small boat or by a small aircraft. And that ability allows us to conduct a different kind of survey. Instead of having a large research vessel and a single long survey, we're able to come to this area for short surveys over and over again throughout the duration of the project, and that way we're able to sample different weather conditions and in different seasons. For the boat surveys, we used either a small fishing vessel or a small research vessel, and we were able to have those platforms out at the point on 26 days so far over the past year and a half, and we're expecting 8 more surveys this year before we are finished with our sampling. Here in this round calendar you can see how many surveys in which month of the year we're able to conduct so far. Once the boat is at the point, first order of business in the morning is to actually visually find the north wall. Here you have some examples of what it usually looks like from the boat. It's usually easily identifiable by sight due to either color change across the front or wave roughness change or maybe some sargassum or sleek along the front. Either way, once we found it, we would drop a drifter into it, which we would use as a sort of an anchor for the survey. And then throughout the day, we would survey across the front at the location of the drifter, turning this survey into a one-day-long Lagrangian survey of the front. For the underwater surveys across the front, our two primary instruments were the ADCP for vertical profiling of the current, and also the vertical microstructure profiler from Rockland Scientific, which was equipped with micro-CTD, with shear probes for dissipation rate estimates, and with ocean color sensors. We would use that profiler in a tow-yaw mode across the front, meaning the boat is moving with constant speed while the profiler is lowered down and then pulled back up time and again without retrieving onto the deck. That allowed us to collect samples down to 80 meters about every 500 meters across the front. Here are the results of a typical underwater survey across the front. We see a sharp drop-off in sea surface temperature about 5 degrees over just 1 kilometer. However, that colder shelf water is quite shallow. Below it, we still have warm Gulf Stream water, which intrudes further inshore. It can reach quite far. We've seen warm Gulf Stream water sitting on top of the shelf tens of kilometers towards the shore from the front. The current profiling tells us a different story. The gradient across the front is quite strong, especially at the surface, but even at depth the current magnitude decays over a few kilometers, so that warm intrusion is much slower than the Gulf Stream velocity. Another important interaction that we see here is taking place about 80 meters below the surface front. This is where the Gulf Stream water is interacting with deeper, colder ocean water, and that interaction is clearly producing a huge spike in turbulent kinetic energy, presumably due to friction. Now, we're not particularly interested in this process for this study, so going forward I'll be cutting off everything below 50 meters and we'll just focus on the water column from 0 to 50 meters. Here in the top row we're looking at the same case as in the previous slide, only the top 50 meters of it. In the second row we're looking at a different case from a different day, but that happened to have very similar conditions, meaning that the temperature profile is very similar, the velocity profile also looks similar. However, look at the dissipation rate. There's a lot more of it in the second case. Now, why is that? Well, I'm thinking this might be because there's a stronger velocity gradient across the boundary over here, and perhaps we're exceeding some sort of a critical Richter set number here that is triggering for this front to become unstable and start losing all of this energy. In case number 3, we're seeing very different structure of the north wall. It's pretty much vertical here, separating the fast and the slow waters. The temperature is uniform across the front except for a thin sliver of colder water on the shelf side, and of course all of the dissipation is focused at the current shear. In the fourth case, we're looking at a different scenario here. In the previous cases, we saw shelf water leaning over the Gulf Stream water. Well, here it's the other way around. The slope reverses the sign. And these types of cases tend to be a lot more unstable, generating far more dissipation on the lower right plot here. On this slide, we can take a look at some of the more unusual cases that we've encountered. This one was, these two surveys were taken back to back on the same day. And what was interesting here is how things changed very quickly within an hour or two between them. The underwater structure, to thermal structure and dissipation structure actually looks similar on these plots. But what was strikingly different on the day of the survey is the sea surface temperature signal here. This is what it looked like on the first survey, but then when we turned around and followed the same track, at some point it started looking very different. It went different direction on the second survey, and we never really regained the warm Gulf Stream temperatures here. And it turned out what happened is over just a few hours, this thin layer of cold water appeared all over the Gulf Stream surface, preventing us from seeing those warm sea surface temperatures again. And then there was this very unusual case on October 11th. Here we are looking at an interaction between not 2 but 3 water masses. We have the warm Gulf Stream water, the lukewarm shelf water, and then what appears to be a colder, deeper water coming up to the surface and entering this interaction. And the result of this is absolutely dramatic. We have this huge area of intense dissipation. We're talking about 3 kilometers wide and all the way throughout the column. So clearly some sort of an instability and energy loss is taking place here, but it is really hard to understand what it is just based on these cross-frontal surveys. What we really need here is additional source of information, preferably some sort of spatial picture of the submesocales that are happening around this front. So that last case is a perfect illustration and the motivation for why we needed the remote sensing component to these surveys. We had 3 types of platforms for remote sensing: the drones, the satellites, and the manned aircraft. We primarily relied on passive tracers that already exist in the water, such as sea surface temperature, chlorophyll, but we also added dye plumes to enhance some of that tracer signature and to have better control of where it is located. Some of the satellite products are well known and readily available. For example, Satellite SST and Satellite chlorophyll are quite useful in detecting and tracking the north wall of the Gulf Stream. Also, a commercial product called ROFS analysis available for the area we found quite useful to help us interpret the ocean circulation processes that are happening in the area. For example, on this day they explained that there was an intrusion of shelf water along the north wall, and then the recirculation of the Gulf Stream water back to the shelf, like so. And we probably ended up sampling across the wall all three of these masses of water, and that's probably the type of situation that we observed in that last case with intense dissipation. On 2 occasions we were able to time large dye releases with overpasses of high-resolution satellites such as Sentinel-2 and Landsat-7. So here the dye plume was released in this zigzag pattern in and out of the front, and then as you can see the older part of the front is not so visible anymore because dye spent more time in the water and got dispersed. But also you can see that it kind of converges on this front as the time goes by. Now on the Landsat 7 case we don't really see that behavior from a similar dye plume. The plume remains fairly focused and it is not converging. In this case it turned out that the front was divergent, which partially explains why it had such low levels of mixing on either side of the front. So the reason why we know it was divergent is because we released these 6 drifters within the dye plume, 3 on either side of the front, and then we observed them for a few hours. So here's the initial tight group of the drifters, and each red line is hourly location of that group. So towards the end of the day the drifters certainly spread out and fanned out, indicating the divergence in the area. On much smaller scales we were able to observe our dye plumes released across the front by means of drones that were launched and recovered from the boat. Here we're looking at an image that is just 300 meters wide, and the boat releasing the dye went along this line here. Now right away you can see this very strong kink in the dye plume, which indicates a strong and abrupt change in the surface current, and that happens right at the front line, which has lots of sargassum, you can see in the image. Another striking feature here is how much more dispersed the dye is on the shelf side of the front than on the Gulf Stream side of the front. And that is just have to do with the amounts of turbulence and turbulent dissipation. On the shelf side, we found it to be 2 orders of magnitude higher than on the Gulf Stream side in this case. Lastly, here are some fresh photographs of the North Wall taken from the window of the NRL Twin Otter aircraft, which just started flying together with our underwater surveys just this month. We haven't had a chance to process all the imagery properly, but it is acquiring maps of sea surface temperature, chlorophyll, as well as maps of the dye plumes. This brings me to my last summary slide. So we've accomplished 26 surveys across the north wall of the Gulf Stream, 26 and counting. So each underwater survey has CTD, current, turbulence information. Also, a lot of these surveys are accompanied by remote sensing imagery, whether from satellite, manned aircraft, or drone. Our in-depth data analysis is just starting, but we do have some findings, some interesting findings already, having to do with convergent and divergent front, the intensity of the front, and how that relates to the turbulent dissipation underneath. In the future, of course, we are planning to bring these results into the framework used by the modelers and by the theoreticians, so that we can compare and test some of these non-dimensional parameters and calibrate their critical values that trigger various types of frontal instabilities. This is all for now. Thank you for your attention.